Hello ICP class. We're going to be working through a next bit of circuit notes looking at series and parallel circuits. I'm going to go through this a little bit faster than I typically do because you're welcome to pause this video and rewind it and rewatch it kind of as you need. So let's start moving. Now back to a circuit is that there's three parts that make a circuit. You know, you got the power source, closed circuits, and then something to use that energy. Well, what happens when we have three things wired together in a circuit? Well, you can have one of two situations be true. You can either have a series circuit where there's one thing after another, and you can kind of also think of this kind of like a book series where, like, you know, Harry Potter 1, 2, 3, those go in order after each other. So when you're looking at something in series, one wire goes into the next one, and those go in order. The other way is parallel. And we see that there is some branching that's occurring for these three light bulbs, that the wire branches out in three directions and then it comes back together into one. And so this creates what's called series and parallel circuits. Okay, and that's really what we're going to do, is unpack what does the voltage, the current, and the resistance look like when these three are in series or in parallel. Now the only parts of a circuit diagram we're going to look at is the switch, the battery, and the light bulb. We're not really going to worry about the ammeter or a voltmeter quite yet. Since this is e-learning, we're kind of stripping back those things, and we'll worry about those next week when we do the circuitry labs. But then another thing we have here is a switch, a battery, a light bulb, and a resistor. So resistor kind of has this squiggly line. Okay, so that's going to be pretty much it. And so when I start talking about these circuits, we can think of a light bulb and a resistor kind of being the same thing, is that they're both going to slow down that electricity. And so there's a couple things that we notice here. And so resistance total is going to be the total resistance found in that circuit, and that's going to be resistors. You're just going to add them up together. Resistor 1 plus resistor 2 plus resistor 3. And so for each one of these, if they had, let's say, 1 ohm of resistance, 1 ohm of resistance, you would just add those three up, and that would be 3 ohms of resistance in total. The next part would be current, and in series, the total current stays the same. So if we read the current at any point to, let's say, be 1 amp, it would be 1 amp at each of these spots. The current would then be the same. Okay, and the last one would be voltage, and then voltage is the same thing as resistance. It's additive. So if we had 3 volts on our battery and all these resistors are the same, you're going to find there's going to be 1 volt at each one. Now that might be a little confusing, so let's go ahead and use a different number. Let's use, let's say this is a 9 volt battery. There would be 3 volts at each one. I don't want there to be confusion that voltage and resistance are the same thing. Okay? So let's go ahead and then try to put this in practice a little bit. So first thing you do when you're looking at a circuit, is it a simple circuit, a series, or a parallel? And what we see out of this circuit here is that it is a series circuit because each of these go in series with one another. So how do you find the total resistance? Well, resistance total is going to be additive. You're going to be adding all these three up. Resistance 1 plus resistance 2 plus resistance 3. So that's going to be resistance 1. We'll call it the first one. It's going to be 1 plus 2 plus 3. It is going to be 6 ohms. All right. Our total resistance is going to be 6 ohms. Okay. Well, what is the total current? Well, let's change the colors a little bit. And so what we know is we know our voltage total, we know our current total, and we know our resistance total. we notice that this looks very similar to the formula we just introduced, as V equals IR. All I'm saying is that these are totals. So we're going to do what we've done before. This is going to be 12, because 12 comes from our circuit right here. And so 12 equals I total times resistance, and that's going to be 6. Divide both sides by 6. And we get current total comes out to be 2 amps. So total current is going to be, I'm running out of space here, 2 amps. I'm going to erase it just a little bit, and that way I got some space to write. Like I said, if I'm going too fast, you're welcome to write down questions and ask me later, or rewind this video and restart on your own. 2 amps. Okay, what is the current across each resistor? Well, the current across each resistor is going to be the same, because if we look back at our formula here a little bit, we see that in series, these currents are all the same. So if my total current is 2 amps, that means across each resistor, you're going to have 2 amps. So the current at the first resistor is going to be 2 amps. The current at the 2 ohm resistor is going to be 2 amps. And the current at the 3 ohm resistor is going to be 2 amps. So what is the voltage at each resistor? As a hint, apply Ohm's law each separately. Well, the voltage at the first resistor is going to be the current at the first resistor times the resistance of the first resistor. So that's going to be V equals 2, because we got 2 amps right here. Do a little right here. And the resistance is going to be 1 for the 1 ohm resistor. So the voltage at the first one is going to be 2 volts. So this first one is going to have a voltage of 2 volts. There we go. Okay. What about the second one? What's the voltage at the second resistor, the 2 ohm resistor? Well, that's going to be the current at the 2 ohm resistor times the resistance at the 2 ohm resistor. And so that's going to be voltage equals current, which is 2, times resistance 2. So the voltage at this second resistor is going to be 4 volts. Or the 2 ohm resistor. 4 volts. Alright, and the last one, let's do this in red, and let's have to do it down here because I'm going to scrunch it out of time, or out of space. Voltage at the third equals current 3, resistance 3, and that's going to be 2 times 3, 6 volts. Okay, there we go. So what did we looked at totals, and then we broke it down, and then we found out our next parts. Okay, so what I'm going to do now is talk about parallel circuits. Now, parallel circuits work a little bit differently, and so these formulas will always be ready for you. You just got to learn how to use them correctly. And so in parallel, the currents are all going to be the same. So if we have let's say a 1 amp going this way, it's all going to be the same. The current is going to be the same throughout all three. Not the same, sorry, additive. The current's going to be additive because it breaks into 3 different ones. And then they're going to come back together. Since they're going to come back together, you can kind of think of it as like 3 rivers breaking up and then 3 rivers coming back together. So you're going to add those currents together. And then as far as looking at resistance follows this inverse additive rule. Now, as long as you have a calculator handy or you're really good at fractions, this should be pretty straightforward for you. But I'm going to work pretty slowly through this next example, and hopefully you'll be able to follow along. So for resistance in parallel, you're going to do inverse additive rule. So I'm going to start with this formula right here, and then calculate our resistance, our total resistance. So what is total resistance in a parallel circuit? Well, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so let's go ahead and try this out. We have 1 over RT equals 1 over 5, because the first resistor here, I'm going to call this one 1, this one 2, and this one 3. First resistor 5, the second resistor is going to be 7, so it's 1 over 7 plus 1 over 9. Now, I'm going to let you in a little secret. If you have one of these calculators handy, this is a whole lot quicker using one of these calculators. And I want to show you why. That we can actually type this in to our calculators really easily. And we're going to follow a rule, an exponential rule. So what we're actually going to type in is 5 to the negative first plus 7 to the negative first. Now this might look a little funky to you, but what actually this negative 1 means the inverse of. So if you look at 1 over x, it's the same thing as x to the negative first. So all we need to do in our calculator now is type in 5 to the negative first plus 7 to the negative first plus 9 to the negative first. And I get this really funky number. I get 0.4539 And a lot of people think, hey, I'm done. I did that really weird funky thing in my calculator, but I'm done. Well, the problem is this is not resistance total. It's 1 over resistance total. So actually what we're going to do again is we're going to use the negative first button again. And so if I hit RT, that's going to be this number to the negative first. And it's going to get me the answer of 2.2 ohms. Okay, I want you to try this out on your calculator or whatever way you want to use it and figure it out. But try that out and see if you get the same number of me. If not, then hey, Mr. Williams, schedule time with me sometime during class or before 3 o'clock, before I leave for the day, to help figure this out. So resistance total equals 2.2 ohms. All right. Phew, that was a lot of work just for that one. Okay, let's move on to the next one. What is the total current? Well, voltage total equals current total, resistance total. So, what's our total voltage? If we look over here, this is going to be 8. So 8 equals current total times resistance total, what we just found out to be is 2.2. Divide both sides by 2.2. So we get then is current total comes out to be 8 divided by 2.2. And that's going to get me 3.64 amps. Okay. And that's we're looking good, folks. We're moving forward. What is the voltage across each resistor? What's the voltage at each resistor? Well, if we look at kind of what's going on here, we can then say voltage equals current times, so we could use V equals IR here, but the problem we run into is that we don't know what the current is at that one moment. We know resistance over resistance total. So actually, what is the voltage here? And actually, this should be written over here, but it's not. Voltage, when in parallel, are all going to be the same. So what is the voltage across each resistor? That's going to be 8 volts. So each resistor right here is going to have 8 volts of voltage. Okay. And then what is the current at each resistor? What does that current do? What does it do? And it breaks up into 3 separate paths. So our current is going to look a little bit differently. So we know voltage, current equals current times resistance. 8 equals current, which is what we're looking for. And the resistor, the first resistor is 5. So that means our first current is going to come out to be 8 divided by 5. And that's going to be 1.6 amps. Okay, let's move on to the next one. The voltage at the second one is going to be 8 equals I2. Resistor second one is going to be 7. 8 divided by 7 gets me to 1.143 amps. And then the last one is going to be, let's do it in red. And I got to move up just a little bit. The current at the third resistor is going to be 8 equals I3 times, oh, what's my resistance, the third one? 9. 8 divided by 9 gets me 0.89 amps. Okay. Alrighty, folks, that's how you go through a parallel and series circuit. That was a lot I unpacked right there. Good time to ask questions would be for Thursday or Friday, or even after school, Wednesday, Thursday, or Friday, or sometime next week. You guys are awesome. Keep up with it, and hopefully I will see you soon. Take care.